Hello everyone, this is Priyanka K studying at Sri Venkateshwara College of Engineering. Today in this video we'll know about programming techniques for Turing machines, extensions to the basic Turing machine, which is the topic in theory of computations. Firstly, Turing machine TOC. Turing machines are abstract computational method models used to understand the limits of what can be computed. While they are simple in structure programming, a Turing machine requires specific techniques to perform complex tasks. Below are the some key programming techniques of Turing machines. They are state coding, symbol manipulation, moving the head, looping the repetition, decision making, parallel tracks, encoding and decoding data. We'll see about state coding. It uses a set of distinct state to represent different stages of computation. States can be encoded to manage control flow efficiently, such as distinguishing between reading, writing, and branching decisions. When it comes to symbol manipulation, the read write operations, Turing machines use a tape where symbols are read and written. Carefully plan these operations to modify the tape as needed. Markers, we use the special symbols as markers to keep track of specific tape positions such as boundaries or key data. When it comes to moving the head, left right movements and use systematic head movements. Left right movements program the machine to move the tape head in the correct direction after each operation. It uses systematic head movements to traverse or search for specific symbols on the tape. Looping and repetition. Loops can be implemented by revisiting states until a particular condition is met. For example, searching for a symbol. Use conditional transitions to implement loops. For example, like transitioning back to an earlier state unless a target symbol is found. Turing machines are abstract computational models used to understand the limits of what can be computed. While they are simple in structure, programming a Turing machine requires specific techniques to perform complex tasks. Below are some key programming techniques of Turing machines. Decision making, parallel tracks, encoding and decoding of data. In decision making, they use a state transition based on a current tape symbol to branch computations, implement decision making by conditioning on different symbol, read from the tape. Parallel tracks they stimulate multiple tracks on the tape by encoding multiple symbols at each position, allowing for more complex data handling. They are useful for handling multiple data points or maintaining a separate working area on the tape. When it comes to encoding and decoding of data, encode complex data structure or numbers into sequences of symbols, implement decoding logic to interpret these sequences correctly during the computation. A Turing machine is also the modified version of PDA or more powerful than PDA. PDA is a stack, whereas Turing machine uses tape to store symbols. Turing machines recognizes all types of grammar like regular language or type 3 grammar, context free language or type 2 grammar, context sensitive language or type 1 grammar, and unrestricted grammar, that is zero grammar. Turing machine model is a finite automata consisting of read with the following components. It is tape, read write head, and control unit. It is used to store information and is divided into cells. Each cell can store information of only one symbol. The string can be scanned, will be stored from leftmost position of the tape. The string is to be scanned, will be should end with the blank spaces. The tape is assumed to be infinite on both RHS and LHS, that is right hand side and the left hand side of the string. When it comes to read write head, the read write head can read a symbol from where it is pointing into and can write where it points into. The read-write head can move left or right, that is, in both the directions. When it comes to control unit, the reading from tape and writing into tape is determined by control unit. The different moves performed by machine depends on current scanned symbol and the current state. A control unit consults action table or transition table and carry out the task. The various actions performed on Turing machines are they change state from one state to another state. The symbol point into right read write head can be replaced by another symbol. The read write head may move either from left or right. Turing machine can be represented using various notation. It is transition table, instantaneous descriptions, and transition diagram. Uh, the formal definition of Turing machines is given by a set of finite states and a set of alphabets and tape symbols function from Q into to start state, a special symbol indicating blank characters, and the final state. The TM, okay. They are expressed in the form of seven tuples. Q is the finite state of states. T is the tape alphabet. B is the blank symbol. Sigma is the input alphabet. It is a transition function which maps Q into 2 followed by Q into 2, which belongs to R, L, and R. Depending on its present state and present tape alphabet, pointed by the head pointer, it will move to new state, change the tape symbol, may or not, and move head pointer to either left or right. Q naught is the initial state and F is the final state. If any state of F is reached, input string is accepted. Now let us construct a Turing machine for the given expression where Q is Q naught, Q1, Q2 and Q3, and Q naught is the initial state. T equals 1, 0, 1, X, Y and B, where B represents the blank space. And a set of alphabets are 0 and 1, and F is Q3. The transition function is given in table which is shown below. Basic Turing machine are powerful theoretical models of computation, but several extensions can make them more practical or conceptually interesting. These extensions do not increase their computational power, but can improve efficiency, ease of programming, or illustrate computational ideas more effectively. Multi-tape Turing machines. These machines have multiple tapes, each with its own read-write head. Faster implementation of sorting algorithms or simulating stack-based computation. When it comes to non-deterministic Turing machine, at each step, the machine can choose between multiple possible transitions. It can explore many computation paths simultaneously, useful for theoretical analysis such as proving whether a problem is in a non-deterministic polynomial time, solving problems like fiability by exploring all possible configurations in parallel. Multi-dimensional Turing machines. These machines have a tape that extends in two or more dimensions, such as a grid, facilitates spatial computation, such as simulating cellular automata. It can be easier to visualize certain types of algorithm, simulating systems like Conway's Game of Life. When it comes to probabilistic Turing machines, these machines can make random choices during computation. Model randomness in algorithm useful for probabilistic algorithms and studying complexity classes like bounded error probabilistic polynomial time. Randomized algorithms for primarily testing or Monte Carlo simulations. We'll see in solving briefly on this problem. Firstly, consider in this situation the read write head control points to the leftmost zero and let Q not be the start state. In state q naught, replace 0 with x, change state to q1, and move pointer towards right the transition, which is in the form of q naught 0, which is followed by q1, x, and r. And the in the state q1, we have to obtain the leftmost one and have to replace it with y. We need to move pointer or read write control to the leftmost of one. Irrespective of the symbols encountered before that, the machine remains the same state or moves right. In state Q1, if the input symbol is 1, replace 1 with y, change the state to Q2, and move the pointer and move to the left. Now the pointer should move left because 0 is to be replaced by x. So to obtain the leftmost 0, we need to obtain the rightmost x first. So we move the control till we get rightmost x. Once we encounter rightmost x, it means that all the symbols thereafter are already replaced by x. Therefore, control will not move right after replacing z0. Next, to get leftmost 0, replace x with x, change the state to q naught, and move towards right. And then repeat the steps till we get the configuration. Next, after q naught, in the state q naught, if the scan symbol is y, it means that there are no more zeros. If there are no more zeros, we should see that there are no more ones also. For this, we need to change the state to q3, replace y by y, and move the pointer by right hand side. In state q3, we should see there are only y's and there are no ones. For every input y, we should replace with y and remain q in q3 state only. The strings end with infinite number of blank. So in the state q3, once we encounter symbol b, it means that we have end of the string is encountered, and there exists n number of zeros and followed by n number of ones. When it comes to quantum Turing machines, it is a theoretical model that incorporates principles of quantum mechanics. It can efficiently solve for certain problems that are infeasible for classical Turing machines. It provides a framework for understanding quantum computations. When it comes to altering Turing machines, it is a generalization of non-deterministic Turing machines where states can be either existential or universal. uh, Universal states succeed only if all transitions lead to accepting states. Models are parallel computations and can solve problems in case of PS space efficiently. Decision problem in logic, such as quantified Boolean formulas. Thank you.